Now here is the 217 problem number 1. And the first thing it wants us to do is use the chart to view sum for 3 intervals to approximate the volume of the, it says indicate the measure of the unit. So I'm going to make a fake graph here. And I need 0, 2, 5, and 10. And then if I look at these numbers right here, they're decreasing the whole. Make fake graph down, and then I'm going to rectangles so that I can find the area of each rectangle. And there are my 3 rectangles. This base 2 and 3, and because that's between the tick marks, and I'm doing the left Riemann sum. This left, this 50.3. When I get to the next rectangle, it'll be 14.4. When I get to the last rectangle, I'm going to use the 6.5 because that's the left side of them. And it says use a left Riemann sum. So the integral from 0 to 10 dh to do each rectangle. So the base of 2 times 54 base times the height of 14.4 plus 5 times the height of 6.5. And it says that I'm supposed to use units. So I'm taking this base, which is in feet, because it tells me over here in the chart it's feet, and the height is feet squared. So I'm taking base times height, so feet times feet squared with cubed, and I should put this, it's everything inside there. You do not need to add that all together, but if you use your calculator, you get 176.3 cubic feet. So that's part A. Part B wants to know is the approximation and over or underestimate. So I'm going back to my picture. So the black's the real thing. The green is the estimate. The green rectangles take up more than the black line would be, just under the black. So we're supposed to tell if it's an over or underestimate. So we would over it. And it says explain because it's a Riemann sum and A of H, or just A, is a decreasing function, which puts it under from the left. So that is part B. Part C says the area in square feet of a horizontal cross section at height h feet is modeled by the function h. So this is kind of doing the exact same thing, except we're no longer using the chart at the top, and we want to find the of the. We're going to use the same 0 to 10 from the first tank, and we're going to use our calculator because 1 and 2 are calculators. So we need to do that the volume is going to be the integral from 0 to 10. And then we're going to have, so this is a Math 9 problem on the calculator, and we're going to have all over e to the 0.2 h dh. Now we're going to be using x's instead of h's, and you're just going to type that into your calculator, and that comes out to be, to the nearest 3 places, 101.325. And again, units measure. So it tells here that the area, the F of H is feet squared. The height is feet, so we're taking feet squared. This is also feet cubed because we're multiplying the base times the height, just like we did on the Riemann sum. And then the last problem says we want water's being pumped in the tank when the tank is at a height of 5 feet, and it tells you that again here. You want H equals 5. Increase height is increasing at a rate of 0.26. That's all this stuff, so I got room to write it. So the height is increasing at a rate, so that is a dH dt. So dH dt is equal to, and it's increasing, so it's positive 0.26. And since it says indicate units of measure, I want to make sure that I realize that feet per minute, write that in there. In the Model C, so this is still area here. Using the Model Part C, find the rate of the volume of water changing with respect to time, and the height is 5 again. So we are looking for dV dt is what we want to find. dV dt, oops, t, sorry. And we want to find that. And that's what we're looking for. We want to find that when H5. So just like the last problem, when we do a problem like this, we're supposed to know the volume is the end of the function we're dealing with right there. So that's my volume. Well, we do the integral we need to get dV dt in there. So derivative of this side with respect to t, that's the part we're looking for. Over here, when you do the integral of f of h dh, I'm going to be left with that same f of h. And then we got to have our dH dt on here because this is an implicit differentiation problem, because we're doing the derivative of but with respect to t. So we need to find, remember we're doing this one, so we're going to plug in f of 5, and we're going to plug that 5 into this function for all your h's. And we know this point is 0.26, and it's still feet per minute here. I hope we remember that this is square feet. So this answer right here, when we get this answer, is going to be square feet. So when you take that times your the f of your 0.26, that comes out to be 1.694 to the nearest 3 places. And we got this feet squared times feet, that is feet cubed. And then that's going to be per minute because that denominator up there is per minute. So cubic feet per minute. And the